All right, I think it's recording. These are my templates for the whiteboard. All right. Welcome to part 3 of analysis of variance, one-way analysis of variance. We've been discussing about the F statistic, but how is it actually computed? The F statistic, as we know, is sorry for that, but I've got it. Where is it? Draw. All right, a line. All right. Oh, let me draw a line. No, just this one. Okay. So F statistic. Okay, let me have that bolder. F statistic is equal to the mean sum of squares between your samples over the mean sum of squares within your samples. That's one of the what do you call nomenclature. There are many books, different books have different names, right? What are the different names of the sum of squares between? Well, and let's measure. Well, first, what are we talking about? Sum of squares. What are these squares? What are the sum of squares? Well, it's the sum of squares between your samples. So it is a sum of squares about the mean of the means, right? The grand mean. So it's like if you have a mean of one of the groups, let's say that group is J, that's the mean of one group, and then you get its difference from the grand mean. This is the grand mean, and you square them. That's the okay. All right. You just square the difference. That's why it's sum of squares, and then you multiply that with the number of items of the J group. So NJ. Right. And you sum for all J's or for all groups. You sum them. So that's actually the sum squares. So this is the sum of squares between groups. Well, if the number of for each group has the same number of items, you can actually just get the sum of squares of xj, the same one that we're talking about. And you multiply it by the number of items of its group, which is a constant, the same, n, with the number of observations in one group. So you can get the sum of the difference of each mean from the grand mean squared times n. So this is also SSB. Right. We're not yet on the MS. This is that one, SSB here. We're not yet on the mean sum because we still have to average them to get the mean. So that's one measure, sum of squares of the mean, right? How is it done? How is it that done? Because when you are given an Excel file, let's say these are, let me see if I can find it there. A, B, C. You have their numbers here. Okay, it need not be equal, but let's say there are equal numbers, 7, 7, so 7 numbers. Yeah, 7. So 2, 3, 4, 5, 6. They have an equal number of items. So you have the mean of its group. So we have A bar is the mean of its group, right? The mean of this one. The average of these numbers, B, the B and C of the average. You have the average. That's the average of A is just this xj here. That's the average of x being xj being A in this case. So yes, the average of A. And this x here is the mean of the mean. So you get the mean of the mean. So the means the average of the averages, or it's the same thing, the average of all the numbers there. Average. So we have an so that this is what it means when in manually, right? You subtract the average from the grand average and you square them. And then you add the next groups, the next group, the difference, the square difference of the next group, exactly what you did from the first group. And you add the third group like that. Yeah. So difference here, the third group, and then you multiply it with the number of objects in one group. So that's your SSB, or your sum of squares between. Maybe it's clearer if you I did not prepare an Excel file. Maybe it's clearer if there's an Excel file for it, so that. But let's just repeat it here so that maybe, for example, let's have some numbers. So just some numbers here, like you clear them. You clear. All right. So A is the group A is like 2 easy numbers, 3 and 1. So what is the mean of this? 4 divided by 3. So A's of bar equals what? It's 3 and 3 divided by 3, 6 divided by 3, 2, right? That's the mean of A. And then there are others, B and the numbers. Whatever number did you have, 1.5, 0.5, 4. So the mean of B, and so on. You have the mean of B, which is 2, 4, 6. It's also 2, right? 6 divided by, which is 2 plus 4. So the mean of B is also 2, but C is, I don't know, 2, 3, then 5, 5. And the mean of C would be 5 plus 5, 10 divided by, the mean of C is 5. It's 10 divided by 3, so 10 over 3, right? So what's 10 over 3? 9/2 is 3, so that would be 3.33, right? It's like that, 3.33. Let's see. So we were saying that to compute for the sum of squares, this is what we are going to compute, sum of squares between. So you get the overall mean first. So the overall mean of this is the mean of the mean. So 2 plus 2 plus 3.3 divided by 3. So 4, 7. So that's 7. The mean, or let's just call that the grand mean. X bar is the grand mean, which is just 2 plus 2 plus 3 or over 3. That's 7.37 divided by 3. So 7.33 over 3. That's the grand mean, right? That's the grand mean. The C is 0.33, so far so good. So what it says to get the sum of squares is that you get the difference of each mean from the grand mean, and then you square them and you sum them. So for group A, or for this one, A bar, the first sum of square would be 2 minus, what's the grand mean? 7.33 over 3. Then you square them so to get rid of the -1. That's 1. And then for B, things like that. It's 2. It's the same. It's 2. For B, it's also 2. I just write here. So you do that for A, B, and C. And for C, you get 3.33 minus the grand mean, 7.33 over 3. Then you square it. And then you sum everything, right? You sum them, and then you multiply it. Yeah, you sum them, you multiply it with the number of items of each. The number is just 3. So that's what it means when we wrote the formula for the sum of squares. The sum of squares between the sum of squares between, or in other words, it's the sum of squares, and later on you get the average. It's the variance of the means. There are 3 means. Yeah, there are three means, right? And there's a variance within them. Yeah, they have a common variant. Of course, we can compute any array of number as a variance, right? 3, so there's a variant, the variance of the mean. Although we are still computing for the sum of squares. Yeah, sum of squares between samples or of the mean. Sum of squares of the means between samples, right? So we have so that's, and sum them, and that's the sum of squares between. So let me just hear that again. The sum of the squares between is just equal to the sum, the n times the sum of each. It's true. This xj is the average of the jth group. In this case, A, B, or C, minus the grand mean. Let's just say like that, the grand mean squared, and multiply by, in this case, 3, n. So we have the sum, the variance, the mean. It's not the variance yet. It's the square, the sum of squares. And we need that to get the variance of the means. So SSB is the distance, right, from the mean, or of each mean from the mean. You square them to get rid of a negative number. And well, to get the sum of squares within samples, it's just the sum of squares of the variant of the sample variance. Sum of squares is the same. So if you know, you have already studied about variance, so it's like the sum of xij minus xj, like this. So squared. So you get the sum of squares of each group, and then you have to get the sum for all groups. So from our example before, you can just xj is the average of the j group, and xi is a member of the j group, right? Like that. So you get the sum of all groups. So operationally again, so remember this formula, but operationally in example, if you're manually or in Excel, this one is like or exactly like let me see. You have numbers A again, B and C. So we have numbers here. Oh, I don't know. I forgot my numbers right there. But we have 2, 3, 1, and so we have this mean is 4 and 2, 6. So the mean is 2, right? That's A bar is 2. I think that's right. So what it says for the sum of squares within is just the sum of xi j minus x of j. Sorry for, I know I just repeat it here. Xi is the sum of the quantity xij minus xj, xj being the mean of the j group. So in this case, you subtract each item of its group, like 2 minus 2, 0. Then you square them. 3 minus 2 is 1, you square it. 1 minus 2 is 1, square them. And you get the sum. So you have that. You get the sum for one group, but you do that for all other groups, right? So for one group, you have the sum. This one, and you sum for all groups, right? So you've got this sum of squares within. So for this one, for the first group, it's like the operational definition or the would be 2 minus 2 squared plus 3 minus 2 squared plus 1 minus 2 squared. That's how you operationalize this, right? And so we have the sum here. Okay, it's for A, and then for B, you do the same as you did in A, and for C as well. Then you sum them all. Right? Mm-hmm. Yeah. So that's how you find it, and then how do you find the mean? Because just the mean sum of square. So what you need in F is all right, and clear again. All right, the F says mean sum of squares between over the mean sum of squares mean. So it's the mean sum of squares within. Well, it's just the the degrees of freedom of the numerator. Or I mean the sum of squares. This is the sum of squares between over the degrees of freedom of the numerator over the sum of squares within divided by the degrees of freedom of the denominator. So how do you find it? How do you find the degrees of freedom of the numerator? Well, the degrees of freedom, the numerator is the sum of squares between, and their degrees of freedom is just k minus 1. So there are three groups. 3 is k, and k minus 1 is 2. So let's say three groups, A, B, and C. So k is 3. So the degrees of freedom, therefore, of the numerator is 3 minus 1 is 2. And the degrees of freedom of the denominator, the sum of squares within, is the total number of items of your groups. They're 30 or 40 or 50 minus k. So degrees of freedom of the denominator is the total number, the n, the total number of your, the n minus k, the total number of samples. So if you have 30, 30 minus k, 3, then 27 is your df for the denominator. And then that's how these numbers are what you divide the sum squares with to get the mean sum squares. So you can get the F statistics. And then of course, after getting the F statistic, you can find there are, pre-prepared tables giving the probability the probability distribution of F, right? So let me just share with you maybe a table like that. So we have the F, we're given the degrees of freedom, of course, 2 and 27 here, in this case, 27 if you have 30. So, and we have a probability distribution given these 2 degrees of freedom. There are prepared tables for that. Can I just show some of my all the prepared tables? I don't know, it's topology here. All right, no, not the one that I want. Well, well, I can just search for it, or maybe here. Here, is it here? Here. Oh no. No, it's not. So wow. Sorry for that. Oh, sorry for that. Now I can no longer go back to our whiteboard. All right. How do I go back to the whiteboard again? Okay, go back to the whiteboard. There. I know it is not the whiteboard. Wow. It's a problem with just learning how to use this tool. Okay, go back to the whiteboard. Back. It should say back to the whiteboard. So wow, I don't know. So let's pause this for a while so that. But that's what I'm talking about is that there is a table for the f given degrees of freedom, the 2 degrees of freedom, the numerator and the denominator, and there are tables of the f distribution. I don't know how to go back, so please help. Um, sharing. Where is that? Oh God, mouse, and then I should go here, and then I should go here, but zoom, and then I don't even know. Wow, the problem with not mastering this, and but we're about to end the discussion, so maybe I'll just use this one. So my famous drawing here. Okay, all right. Oh, there. No. Oh, no, untitled. All right, clear the drawings. All right, so, so you can use paint. So that's it. You have your table for the F, and you just get the probability of any F occurring greater than your F. And it's small, and you reject it. You reject your null hypothesis. Sure, computed F, and you get its probability. You have tables, right? You have tables. I'll show you the table. The table should be somewhere here, like F distribution tables, F distribution table. All right, so many, yeah, things like this. So there are so many in the internet. There are so many. There's so many F distribution table. How to use it? Yeah, things like that. Like degrees of freedom, and the degree of freedom, and the degree of freedom 1. This is the numerator, and this is the denominator's degrees of freedom. So this is that gives a probability that the F values that gives the probability of 0.1 to the right of that F value. And then there are, of course, other. So this is 0.05 to the right of the F value. So these are your numerators, degrees of freedom, and then the denominators, degrees of freedom on this first column. On the top row is the second to the top. No, the top row is the degrees of freedom, and it gives you the F value that gives a 0.05 probability to the right of that whatever F value is that. So once you know your degrees of freedom, your 2 degrees of freedom, you should know, because that's the intersection, you should know your F, and you should know your, and then you compare that. These are the F critical values. Compare that to your F. So if you know how to use the T that we have discussed earlier, you should be able to use the F as well. The same thing. All right. Okay. Thank you very much. An example would be like, for example, these are the F critical value. You have 30 samples. Your degrees of freedom is 27, and your is 2. Your denominator is 2 and 27 here. So you have 30, right? So this is your critical F value here, 3.35. This 3.35, anything that's to the right of this gives a probability of less than 0.05. What it means. So with n equals 30, df of the denominator is 27. df of the numerator, if there are 3, it would be 2. If there are 3 samples, 3 groups, would be 2 and 27. So that's what you will see. And if you have chosen a significance level of 0.05, then you get a table that gives that. So what did it say? What does it say in the table? With 2 degrees of freedom in the numerator and 27 degrees of freedom is 3.35 41. So that's your critical F. Gives you a probability of 0.35 to the right. So that's what's that again? 27, 3.3541. So that should be 3. This critical F is 3.3541. It gives a probability of 0.05 with all these degrees of freedom. 27 for the numerator and 2 for the denominator. 2 for the numerator and 27 for the denominator. This is the critical value, 3.341. So if you get an F that's 4, so that's to the right of 3.3541, then you know, of course, that the probability to the right of 4 it would be less than 0.05. It means that's very small probability that you get a higher F than your F. Hello? Sorry. Espera. Espera, es que estoy grabando una clase. Sige. Sorry for that break. I have an emergency call. So that's how you test your hypothesis. You just compare your computed F with your critical F. If If your computed f is to the right of your critical f, then it means that the probability of yet higher f than your f will be very small if you have chosen your critical f to be at 0.05, because this becomes smaller and smaller, right? To the right, probability becomes smaller and smaller. That's how it's done to test your hypothesis. Now, if it's to the left, then it's big, right? If you have an f that's to the right of 3.05, like 2, if you have a, what if you have a 2, then you know that's greater than 0.05. The probability of this is greater than 0.05, and it's too big. I mean, there's a high probability of getting higher f or going mean differences or mean variances. Yeah, a higher variances or more varied, if so to speak, means. The probability is too high, and you won't conclude or your mean are actually this different. You have to reject you have to accept the equality, or there's no proof that the mean are not equal. There's no enough proof, so you failed to reject the equality hypothesis in that case. If to the right of point, to the left of 0.35 here. Example 2, right? Okay, if that's not clear, I'll repeat this again if in class. Okay. Thank you.